Okay, welcome to Klein's Calculus. Today we're going to look at lesson 4-6 and we're going to look at example 2, a rising balloon. I was too lazy to write it down, so we're going to start by reading the problem. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? We are going to look at this related rate problem using this organizer. What we're going to be doing is we will draw and label a picture to understand our information. Then we will state in words and in variables what we intend to find. We'll write down all the information we're given, and there's two things to look at. What's general information that's never changing, and what is changing with time, but at that point in time, what did they tell us? Then we look at this stuff, we look at this, we don't look at things changing at that point in time, and we write an equation that relates the variables, and we can use any constants that don't change. Then we're doing just like the max-min problems. We take the derivative, but we have to do it with respect to time, and then we'll put in our point of time information to answer the question. So this is the general form that you're going to use. I've put it on a large whiteboard so that we can kind of work through this together, and let's see how this works out. Well, what we're given in example 2 is we have a hot air balloon that's rising. So we have a balloon, and it's coming up from a liftoff point, and 500 feet away from it is a rangefinder. And it's got its bead on the balloon. Let's make a little bigger balloon so it reaches it. And the angle of the rangefinder as the balloon goes up is changing. So that's just theta. And the height of the balloon as the balloon rises is changing. So the only constant we've got here is the 500 feet. So under my general and constant information, I'm going to say my horizontal distance is going to be 500 feet all the time. That never changes. It says the thing we want to find is how fast is the balloon rising. So we'll write down how fast is the balloon rising at the moment in question. And we would denote that in symbols, since the height tells you about the balloon. It's the change in height over the change in time. That's what you would say is a variable to describe how fast the balloon was rising. Now, they also told us at the point in time we're interested, the elevation angle, theta, equals pi over 4. And they also said the change in the angle was increasing at the rate of 0.14 radians. So that would be the change in theta over time equals 0.14 radians per minute. So I'm going to make sure I've got that down, and then I wrote my units, because that's going to be important later, okay? So then I look at this picture, and I look at my constant information, and I say, what kind of relationship do I see? And you might have to look at anything. You got to look at your geometry formulas, your trig formulas. I see a right triangle. We know balloons rise straight up without a wind. We're assuming that. So I can see a tangent relationship. The tangent of theta is the opposite over the hypotenuse. So that's the equation I will write. So we write an equation relating the variables, so I know the tangent of theta equals the hypotenuse over 500, because I can only use my constant information and the variables in the picture. And now I just take the derivative of that. And I take the derivative of both sides. So it's just like implicit differentiation, but we're always doing it with respect to time. So the derivative of the tangent is the secant squared of theta, and it's going to be times the change in theta over the change in time. And that equals, and the derivative of h over 500 is 1 over 500, but it's the derivative, the change in h with respect to time. So we have to make sure we've got our dH, d theta, d time, and the change in theta over the change in time. Now that we've taken the derivative, after taking the derivative, we can, so after finding the derivative, then put in change of time info. So now I can go back to this point in time box I've got, and I can say, okay, I've got my secant squared, and instead of theta, I'm going to put in pi over 4 times, and the change in theta was 0.14, and that equals 1 over 500 times the change in height over the change in time. Well, I'll make it a little simpler, and I'll just put my 500 here. Because now this is what I want to find, the change in height over the change in time. Well, when I think about secant squared, I have to remember, I'm looking at pi over 4, so I'm going to look at that right triangle, that isosceles right, because this would be pi over 4, 1, 1, square root of 2, and I know the secant's the reciprocal of the cosine. Cosine is going to be the opposite over the hypotenuse, or, adjacent over the hypotenuse. So that makes the secant the hypotenuse over the adjacent. In this case, it would be square root of 2 over 1. So, easy enough here, I've got 500 times the square root of 2 squared times 0.14 equals the change in height over the change in time. Square root of 2 squared is 2 times 500 is 1,000 times 0.14 equals change in height over change in time. And that's just going to be 140 equals my change in height over the change in time. Now you can't be done here. You need to give your solution in a sentence. And since the thing we wanted to find was how fast is the balloon rising at the moment in question, a good way to answer it would be to say, at the moment in question, the balloon is rising. So that's what we're going to write here. At the moment in question, the balloon is rising, and here's my answer, 140. Don't be done there. What are my units? Well, I know my distance was in feet, and my change in angle over time was in minutes. So I've got feet per minute for my answer. Don't forget your units. So here's the answer, and we have to have that. So what we're going to do, anytime we got a related problem, draw a picture. Step 1, draw a picture. Label the constant stuff and anything that's changing, throw a variable in. State what you're asked to find. Put it in words and in variables. So that the words are going to help you at the end when you're answering the question. The variables are going to help you as you're going through the work. Looking at your picture, figure out what's constant information, what never changes, and what's point in time information. Find a relationship in your picture, an equation you can write relating this stuff. You can only use the constant. You can't use any point in time information until you've taken your derivative. Found our relationship, take the derivative. Now plug in your moment in time stuff. Simplify, simplify, simplify. Answer the question in a sentence. So hopefully this is going to help you, and we will see you in class.